All right, continuing our talking about optics. I know you guys are not sad that you didn't get to do a lab activity yesterday, but I am, because I think there's a lot of value in actually doing these and seeing how the light works. We do still have an optics lab next week to give you some experience. We talked yesterday in lab about how we form images with a lens, how we can draw diagrams to see where the image is formed, and how we can use an equation that derives from geometry to find where the image is formed. So today we're going to move forward on what we learned yesterday and talk about what happens when you have multiple lens systems. But we're going to start with the eyeball. So angular magnification is what we think of when we talk about magnification in a practical sense. When I look at something like the moon with my naked eye, it makes a certain size. And some people think that the moon is bigger on the horizon than it is when it's up in the sky. Have you experienced that or heard people talk about that? The reason is not because it's bigger, but because of perspective. When it's on the horizon, you might see the moon behind a tree. And you know, while that tree is like this big, you know, it's 100 feet tall or something, you have a very real sense of the size of it. And then you look at the moon, you're like, wow, the moon is bigger than that tree, and it's so far away, and you're like, wow, it's really big. Your brain says that's big because you're seeing it in perspective to other things that you know the size of. Whereas when it's overhead, you're only seeing it with respect to stars. You don't have a sense of how big it is. All you have is the angle it makes up. And you tend to think, with all this empty space, it's a smaller thing. The size is actually the same, except for one little itty-bitty thing. When the sun rises, do you know where the sun is? Okay, in the east. That's a very good answer. It's not the one I was looking for, but it's an absolutely correct answer. Hence, you can't ever say no. No, that's not it. When somebody gives you the right answer, just not the one you're looking for. Okay, here's the Earth. And we are going to put Arlene right here. And so she sees the sun coming up in the east. So I don't even know which direction I should mark as east on this. Let's call this east. So she sees the sun rising, so the sun is right here. But that's where she sees it. Where is it really? It's a little bit lower. In reality, the sun's going to be somewhere like here. Because the light from the sun, of course, light from the sun is going out in all directions. And when it gets into the Earth's atmosphere, remember we talked about mirages, the light bending because you have a differing index of refraction. Well, out there, before it gets to the Earth's atmosphere, the index of refraction is 1, exactly, because it's going through vacuum. When it gets into the Earth's atmosphere, the index of refraction goes up a little bit because now it's going through a medium. And when you have a higher index of refraction or a slower speed, what happens to the direction of the light? It bends which way? Toward normal or away from normal? Toward. If you go into something slower, something with higher index of refraction, it bends toward normal. So we have the light that's coming like this, and it hits the Earth's atmosphere. And so the normal for the atmosphere is like this, and it bends toward normal. So it comes out more like that. And so it turns out that we actually are seeing the sun on the horizon when it's below the horizon. And so the sun kind of gets squished in the direction perpendicular to the horizon as we see it. It's not changing the horizontal size, but it's making it a little bit smaller in the vertical direction. And you might have noticed that when the sun is rising or setting that it kind of looks more like a mushroom than part of a sphere. Okay, so coming back to this, 5 minutes to say, we measure the size of an object when we're looking at a star by the angle it makes with our eyeball. So one of the things that we do like in astronomy is we say, okay, if I hold my hand at arm's length, the moon is about the same size as my finger. So the angle that my finger makes, that is from here to here, coming to my eye, is the angular size of the moon. So we measure the angular size. Here's, you guys are going to dig the physics eyeball eventually. So here's an object, and it makes an angle with the eyeball. And the bigger that angle, the bigger we perceive its size. So that's how we measure size. Now, if I have a magnifier, like binoculars, those binoculars are going to increase the angle that the image makes with my eye compared to what it would have made if I didn't have the binoculars. So that's what a magnifier is doing. It's increasing the angle. Now, I have a clicker question that's coming up in just a moment. So here is an actual nice picture. If I have something really tiny, like let's say that a little tiny bug lands on my finger and I want to see the bug in details, what do I do with my finger? I bring it closer. I bring it closer because that same size bug is going to make a bigger angle as I bring it closer. If it makes a bigger angle, it looks bigger and I'll be able to see more detail unless I bring it closer than my near point. If I bring it close to my near point, then it's not in focus. Well, I've done nothing useful then. So we typically will simply bring something closer to get our maximum angle possible. Well, if I want to get a bigger angle than that, I'm going to have to find a way to use optics like lenses to make it take a bigger angle. And so we're going to talk about 3 kinds of magnifiers. The first one will be a magnifying glass. That is a simple lens that I use to magnify. The second one will be a microscope, and the third one a telescope. Now let's talk about the words. I'm pretty sure I have a slide coming up that will ask about the words. Microscope. What's the point of a microscope? It's what? Okay, to see small things. Micro is a prefix that means small. What is the point of a telescope? To see far things. So tele means far. So the purpose of a microscope and a telescope, I mean, when I was a kid, I thought that they were opposites. That, a microscope was for small things and telescope was for big things. That's not really the purpose here. The things you look at with a telescope are generally big. But the point of the telescope is to make something that's far make a bigger angle, whereas the point of a microscope is to take something that is small and to have it make a bigger angle. Both of them are trying to magnify to make bigger angles, but you have something that's far, you can't get close to it. If you're trying to look at a feature on the moon, if you could just get close to the moon, you certainly wouldn't need any special scope. But from this distance, we need a telescope to make that far thing look like it's closer, making a bigger angle. And in all cases, we're going to measure the magnification as the angular magnification. So it'll be the angle we get when we look through our optical device divided by the angle we would have seen if we just looked at it without our device. And we're going to start by using a simple magnifier. This equation here is the same as what I wrote there. The difference is I put theta prime for the angle with my device. Theta regular was the normal. This is a question I've already answered just to make sure that you're with me. Make sure you're, paying a modicum of attention. Let's see if it'll work this time. Okay. What do you naturally do when you want to see something in greater detail? Right? This is something you could have answered without us discussing it all because it's what you naturally do. Not, oh, I learned something new. And because it took me a while to get this available for answers, I'll tell you people who have an answer so you can be aware. So Rebecca, Edward, okay, now just Edward. Corso. Do you have your Corso? Everyone has answered but Corso. There you go. You're in. Okay, so our answers here. I don't know how that happened. Clearly that person's not with us in body. You don't move it farther from your eye to see a bigger angle. You move it closer. I don't know how anyone would have answered that. These other ones, at least, blink rapidly. I never answered Amanda's question in lab yesterday. I suddenly realized. Let me see what Christian has, and then.
I didn't put B, but technically, if you're trying to read like a book up in front of you, you have to move it away and actually read the words.
Okay.
The question is to see something in greater detail.
Okay, so what he's saying is, okay, maybe it could be an issue with the near point. If you have something closer than the near point, where we talked about the near point yesterday, if you have it closer than the near point, then it's just blurry, it's not in focus. And so you're moving it out to get it past the near point so it's in focus. That's what you're saying? Yeah. Okay, that is a reasonable explanation for how somebody would have come up with that if they weren't listening. And I know he said that he didn't answer that, so I'm clearly not saying you. Let me answer Amanda's question from yesterday really quickly. Why does squinting help us to see something better? It helps us to see something better because when light goes through our eyeball, we have it going through that little hole, the iris. Well, the pupil is the name for the hole. And so let's say we have a tree here. There's my tree. And our eyeball is out here. And so light from that tree, let's say light from the top of the tree goes in, and some goes in there, and some goes in there. Now, my lines aren't perfect, but if you get to the retina, so let's say here's the retina, you would have the top of the tree is in some region like this. And likewise, the bottom of the tree would be in some region like this. So even if your lens does nothing, if you do no focusing whatsoever, you can differentiate where the top of the tree is and the bottom of the tree because of that, the size of the opening in your eyeball. And if the size of the opening gets smaller, what's it going to do to the size of the region that I scratched out for the top and the bottom? It's going to make them smaller. And so if that size of the hole gets small enough, it turns out that you're always going to have a perfect focus because you would only have one place where the top is, only one place where the bottom is, and everything will be spread out. And so even if your eye isn't focusing well, the smaller the opening, the better the focus will be. And so that's why you can see better squinting because you're making your opening smaller. So even with the eye not focusing well, you're getting better separation between pieces of the image. We say that we're increasing the depth of field, we're increasing the range that looks in focus. Okay, so I said I would talk about it and didn't remember until just now. We always have the blinking. I thought the blinking closing the eyes. Okay. These ambient light ones, if you increase the ambient light, your brain has a natural response of closing down that iris, which is going to help you to focus better. So that is something that would help you to see better by having brighter light to make the iris smaller. But that's not the one that we naturally do. And blinking rapidly, stop blinking. I'm not really sure how those might truly affect. It's just I was thinking blinking and closing the eye. Okay, so the simple magnifier. The basis of using the simple magnifier, I don't even know the words on this. I'm just going past them. Basis of using the simple magnifier is that we are going to say, what's the biggest angle this object can make, which means I'm going to bring it all the way up to the near point. If it's at the near point, it's going to make the biggest possible angle with my eye where I can see detail. Anything closer, it's going to be fuzzy, be bigger angle, but fuzzy. Anything farther, hopefully it'd be clear, but it would be smaller angle, so less detail. Then I'm going to compare it to what I can see if I use a lens that will make a virtual image that I can focus on. So where do I want that virtual image to be formed? If I'm going to use a magnifying lens and I want to magnify as much as I can, where do I want the virtual image to be formed? Would I want the virtual image close to my eye or far from my eye? I saw your mouth move that again, but I did not hear. Okay, close. If it's closer, like if I bring that virtual image up to the near point, I will have the image as close to my eye as I can see again. And so that should be my best. And it is my best, but it turns out that's not what we aim for. We do not aim for the best magnification when we use simple magnifiers. And we'll work out why in a few moments. But what we generally do is we say, let's try this. Let's put the, okay, this is starting the actual derivation. I have the derivation like all worked out in slides here. So let's start by saying, without the eyeglass, I'm going to say, what's the biggest angle I can make with my eye? So I bring the object up to the near point, and I have an angle here unaided that is tangent of theta is equal to the opposite side, which is the height, divided by the adjacent side, which is the near point. Just using n for near point today instead of np. Now, if this is a small object, and you know what, you only use a magnifier for small objects. We don't use a magnifier for something like a meter stick. If it's a small object, then that's going to be a small angle, and we can use a small angle approximation that says tangent theta is approximately equal to theta. What units is theta in if I make that approximation? Radians. That approximation is for radians. So the angle is approximately equal to the height of my object divided by my near point. Now I get my magnifier, and I'm going to put the object at the focal length of the magnifying lens. I put the lens close to my eye. For our calculations with a simple magnifier, we say we put the lens right next to the eye. Yesterday in lab, I said eyeglasses are 2 centimeters away from the eye. Why the difference? We're just being a little more careful with the eyeglass calculation than we are with the simple magnifier calculation. So this is saying you have the magnifier right next to your eye, not out 8 inches from your eye. So you put the object at the focal point. If you put the object at the focal point of the lens, where's the image going to be formed? Let's do this mathematically. We had an equation that said 1 over focal length is equal to 1 over distance object plus 1 over distance image. And so we said, let's put object at the focal length. So I have 1 over f equals 1 over f plus 1 over d image. What is d image in this case? What is that? Lauren is mouthing words to me. I don't see anyone else responding. One over zero. If you take math classes, you learn to call this undefined. If you take physics classes, you learn to call it plus or minus infinity. It's approaching plus or minus infinity if you're in a math class. So in physics here, we'll say it forms an image infinitely far away. Plus or minus, what this means is that we have parallel rays. Parallel rays, if I focus at infinity, I'm focusing on parallel rays. Why would we want to do that? If your eyeball is relaxed, what are you focusing on? You're focusing on things infinitely far away if you have ideal vision. And so the idea here is we're going to put the object so the image is at an infinite position so my eyeball can relax. So the reason we don't go for maximum magnification is because we want the eyeball to relax. Now we're going to have to justify this to see what difference it makes. Otherwise, we're a little bit, did we make the right choice or not? So we're going to have an image infinitely far away, the object at the focal length. If I draw rays, the ray that goes from the tip of the object to my eye is going to extrapolate back to my image. And so my image is going to have exactly the same angle as if I just take the angle going from the tip of my object to my eyeball here. And so just like we did before, tangent of theta aided is equal to the opposite side. What's the opposite side in this triangle? Opposite to the theta aided? It's the height. And what's the adjacent side? The focal length, because I place my object at the focal length of my lens. So there's the tangent for the angle aided. And once again, with the small angle approximation, that's approximately equal to the angle aided. And now I'm ready to do the magnification. Magnification is the angle aided divided by the angle unaided. So we just put in the two angles we found. The height of my object over the focal length of my lens divided by the height of my object over my near point. The height of objects are going to cancel. And I just have the near point over the focal length. So that's the magnification you get from a lens. What kind of focal length is going to give you more magnification? A longer focal length or a shorter focal length? Shorter focal length, because you're dividing by that. So the shorter the focal length, the bigger the magnification you're going to get from a simple magnifier. How do you make a shorter focal length lens? You make it more like that. Okay, cool story. When I was in graduate school, my professor bought a lens that was shaped like a sphere. And that was to give it a really short focal length. Its focal length was supposed to make it so it came to a focus about here. Great. It's made out of quartz glass because we were using ultraviolet lasers. And the ultraviolet light, of course, needs to have something that's transparent to the ultraviolet light. Fine. Only one problem occurred. When we put the laser light through that lens, it blew up. Why? Because the focal length was calculated for visible wavelengths. Remember, we talked about the index refraction changes with the frequency or with the wavelength. And for ultraviolet light, the focal point was inside of our lens. And so we focused all of that high energy ultraviolet light about here and broke it up. Just talking about how you get a shorter focal length. It was pretty funny. It was a lot of money shot to heck and first time we used it. But good times, good times. That's how we calculate the magnification of a simple magnifier. It's actually really simple. But I said, this is not the maximum magnification you could get from the simple magnifier. What would give me the maximum magnification? Where do I want the image to be for maximum magnification? Where did I want the object for maximum angular size? I want it as close as I can get it and still focus on it. So at the near point. So for maximum magnification, I would want to move my object closer so it makes an image at the near point. So we're going to look at that next. Going to do that before I go to that question. I may have this worked out in slides after the question, but I want to do it now. So we're going to have the same initial angle here, but now we're going to draw a new picture and have, there's the height of my object. Here's my image. Here's my lens. And now I'm going to have this distance here is the near point distance. How can I calculate the theta aided from this diagram? I know the height here, but not the distance. I know the distance here, but not the height. Go ahead. I can make some relationships between them, but I only have two sides, so I'd have two unknowns. What we do is we use the thin lens equation. So here's my distance object. Distance image is equal to minus n. Why is it minus? Yeah, it's on the wrong side of the lens, right? That's a virtual image. And so I can take this and say, well, let's just solve this baby for 1 over distance object. In fact, let's solve it for, 1 over distance object is equal to 1 over focal length minus 1 over distance image equals 1 over focal length minus 1 over minus n. Right, where I substituted distance image is equal to minus n there. Theta aided, using my small angle approximation, theta aided should be equal to h over distance object. Right, h is the height, distance object is the distance. So I had here tangent theta aided equals h over distance object. So there's my angle aided. Now I just go back to this equation. And so that's going to be on top and on bottom that. Well, that's actually really easy. Right, I just broke it up into two different fractions. The first one is what we found before. So the maximum magnification you can get with that simple magnifier is equal to your near point divided by the focal length of the simple magnifier plus 1. Now, your near point being about 25 centimeters, if you have a focal length of 5 for your lens, 5 centimeters, then you would be able to go from 25 over 5, which is 5, plus 1 to 6. So you would have a gain of going from 5 to 6 for your magnification. That is a 20% increase in magnification. But is it worth it for the eye strain? Most people say no. So that's why we generally do the calculation for the object at infinity. You can easily get an eyepiece that gives you a 10 times magnification. That would only be a 10% improvement if you were using the most strain on your eye possible. Why strain your eye? If you're going to be spending all day looking through an eyepiece, you don't want to have eye strain. That's why we use the lower magnification that you get with the object infinitely far, or the image infinitely far away. It's to save eye strain. Okay, now our next clicker question. As discussed, the object is placed at the focal point of the simple magnifier. Where's the image produced by the simple magnifier? Okay, waiting on Brandon. All right. We had no majority on this. So turn to your neighbor and talk about this. Where is the image going to be formed if the object is at the focal point of the lens? Okay, let's try it again. So it's open for re-answering. Okay, it came out a lot better the second time. So rather than ask somebody, let's just go to the calculation that we did just a moment ago. 1 over f equals 1 over distance object plus 1 over distance image. If distance object is equal to f, then 1 over distance image is equal to 1 over f minus 1 over distance object equals 1 over f minus 1 over f equals 0. So that gives you distance image equals 1 over 0. And I said, in physics, we just say that's plus or minus infinity. It's in truth approaching plus or minus infinity. So the image is infinitely far away. That's the result of having parallel rays. And we had all of that just a few moments ago. It's an important concept. It's important to be able to use this equation to deduce it. Now, I'm going to go to, I don't think I have, I know that this image came out right when I put it in. It must be something like when I put it on my tablet that it doesn't come out right, but that's okay. Let's just take this, and I want to do a problem now. Let's say I have an object that's a small object, has a height equal to 1.2 millimeters, and I want to see the biggest angle possible. So question number 1, what's the maximum angle that I can see this with? The maximum angle where I can focus on it and see whatever detail my eye can see. So go ahead and calculate that quickly. When you have an answer, raise your hand. Assume you have a normal eyeball. So near point is 25 centimeters and far point is infinity. You got a question? Yeah. Remember, it's in radians to begin with. Okay, well, we'd better move on or we're not going to get anywhere. Not that small. I pulled a card and it's Arlene. What did you get, Arlene?
0.0048.
She got it right. And how did you do that, Arlene? Did you draw a picture? No. If you had, your picture would have looked like this. Here's the height of my object. Here's the near point, because to get the maximum in focus, we're going to have it at the closest point is the near point. And so this angle here, I'm just going to put un here instead of putting the whole thing. I have tangent of theta unaided is equal to opposite over adjacent. And for small angles, that's just approximately equal to theta unaided. Now, if you're wondering if the small angle approximation is appropriate, put your calculator in radians mode and hit tangent on your answer. If you get an answer that's significantly different, then, whoa, small angle approximation wasn't appropriate. If it's fundamentally the same answer, it was appropriate. Okay, that's question number one. Question number two. What's the maximum aided angle with a, gotta change my zoom here. What's the maximum aided angle you can get if you have a focal length of 2.5 centimeters magnifier? Okay. Do you have an answer, Nice? Because you're the card I drew.
I got 0.04.
Okay, so Nice got 0.046. That's not what I get. How did you get it?
You do tangent, intention,
Mhm.
and hash over F.
So inverse tangent?
Yeah. So 1 to so it will be equal out tangent. 0.12 over 2.5.
Okay. That's not it. I just wanted to see, make sure that, it wasn't something. I'll go over. I just wanted to see in case you'd done something that was mostly right and I could point to it quickly. What we've just worked out is the magnification for unaccommodated vision was equal to N over F. And the magnification maximum or accommodated was equal to N over F plus 1. That's what the result of our work right here was. And so using the maximum, that's going to be 25 centimeters for the near point over 2.5 centimeters for the focal length plus 1 is equal to 11. So the maximum magnification will be 11. What is this magnification? That's the theta aided over the theta unaided. So the theta aided is just equal to theta unaided times the maximum magnification. So that's going to be our 0.0048 radians times 11, which is 0.0528 radians. Question?
So you would use the formula you described earlier where it was height over the.
It is going to give you the same answer, but since I just did that, I went to using that solution instead of doing it. So yes, I could have done what you just said. I could have gone to this right here and done height over F plus height over N. And that should have given me exactly the same thing. That would be what was F? 2.5. Should have given me the same answer.